All right, so write a third degree Taylor polynomial. That means we're going to need to go all the way to the third derivative. So I'm just going to write all the derivatives off to the side here. You want to think of this as x to the -2. So you bring the -2 down, and then it'll drop to a -3. So it will look like that. You guys have been really good at following that pattern, though, so I think we're probably okay there. So second derivative, you want to think of that as -2x to the -3rd. So when you bring the -3 down, it'll be +6 and then drop to a -4. And then your third derivative, same kind of pattern, it'll be -24 over x to the 5th. So I just wrote all my derivatives off to the side. Also, you can or not, I always write out the in general format every single time, just because it helps me stay organized. So we want to be centered at 2. So we're going to do f of 2 over 0 factorial x minus 2 to the 0. So that's like everything's a 0 for that one. And then first derivative at 2, 1 factorial x minus 2 to the first, and so on. I'm not going to read all these because that's annoying. And I'm going to run out of room. There we go. I just had to scooch that over a little bit. And then we're just going to go and plug everything in. So for this first one, f of 2. So you're going to plug 2 into that original equation. That would give you a 1/4. All the rest of that goes away. So the entire first term is just 1/4. And I don't need you to simplify any of this down. You can leave it all alone. Okay. So first derivative at 2. 2 cubed would be 8. To be really honest, you want to leave it -2/8. That's fine with me. Over 1 factorial x minus 2 to the first. You can simplify as much as you want or not at all. Again, at this point, like we're past the AP exam, so I don't really care. All right, second derivative at 2. So we're going to plug in 2 here. 2 to the 4th would be 16. So 6/16 over 2 factorial x minus 2 squared. And then the last one, third derivative at 2. 2 to the 5th is 32. So -24 over 32. Honestly, you could leave it 2 to the 5th, though, if you really wanted to. I just didn't because it's going to look really messy there. Over 3 factorial x minus 2 to the 3rd. And this whole thing is your answer. So it can look like as much of a mess as you want. That'll be my problem to grade it. Leave it however you want. All right, number 2, 4th degree Maclaurin polynomial for cosine of x. Actually, these next 3 are the 3 that I told you to memorize: cosine, e, and sine. So cosine x was the even ones. So it starts with 1, it's x to the nothing, minus x squared over 2 factorial, plus x to the 4th over 4 factorial. And I said 4th degree, so you just stop there. Like, that's the answer. That's all you have to do. All right, for this one, I would write out e to the x, and then we're just going to plug in 5x everywhere that there's an x. E is the one where you get everything. It doesn't like alternate or anything, and that's because e is its own derivative. So it's 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial. It's just the first 4 non-zero terms. So then everywhere there's an x, you're going to put a 5x. And again, you don't have to simplify any of it down. In fact, I kind of prefer you just leave it like that because then it won't be wrong. Like, just take out all the x's and replace them with 5x. All right, and then sine alternates, and it's all the odd ones. So it starts with x to the 1st, and then it's minus x to the 3rd over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial. Oh, so that's sine of x. I should have written that out front. And then everywhere that there's an x, we're going to replace it with x to the 4th. Again, just everywhere there's an x, replace it with x to the 4th. You don't have to simplify them down unless you want to. So it's like we're covering the material, like it's still the material, but I'm not asking you to do anything like above and beyond with it. Like just the barest minimum is good enough. Is this coming back to you? Like we haven't lost it already, right? Okay. Good.
It would have been nice though,
Oh, it was none of the ones that you had memorized?
No.
Oh, dang.
Wasn't.
It would have been nice if it had been like E to that.
Right, like, and the next one you will get another two.
Okay, so Maclaurin series for a function is given by this. We want the third derivative at 0. Again, I just write it out every time. It's third derivative at 0 over 3 factorial x to the third is what that term would look like. I guess you could write out the whole thing if you wanted, but I'm just kind of like plucking out that one term. And so we're gonna plug in 3 over here. So that would be x to the third. And if you plug in 3 here, that would give you 15. So it's 1/15 x to the third. And we're just solving for this part. This is what they're asking for. Now this one you do actually kind of have to simplify down a little bit in order to solve it. These are going to cancel. 3 factorial is 6. So you have that. Wait, what was that?
How did you get 1?
Oh, I took 3 and plugged it in. So x to the third, like that's where the x to the third came from. I plugged in 3 for n, and then 5 times 3 was 15, but it's just, it was in the denominator. I just plugged 3 in for n right here.
Okay, yeah, 9.
So like on your test, I think I made it a 4. You'll just plug in 4 or whatever number I made it. And then you just multiply the 6 over. So this part is going to equal 6/15. So you're just getting this part by itself. Like that's what you were asked for. So you're just solving for that part. All right. And then I left a whole lot of room for this. This is your ratio test, find the interval of convergence. Again, these are a bunch of writing, but I actually kind of like them because they turn out the same every single time. You just have to write it out. So first we're going to plug in n plus 1. So everywhere that there's an n, you're going to put an n plus 1. And then that goes over the series itself. Okay, and then we're going to reciprocate this. So this stuff's going to come up to the top. All the stuff in the middle is going to stay on the bottom. And again, just try to line it up. And I ran out of room. I'm going to have to come down to the next line. But the next thing would be to look for what cancels out. And a lot is going to cancel out. So first of all, the 4s will just go away, which is kind of nice. We'll have 1x minus 5 left. It'll be on the top. The n squared and the n plus 1 squared, you really can't do anything with. But then you have one more -4, which is going to be on the bottom. And I kind of wrote that in front because the next thing that we're going to do is the limit. So you write it, you reciprocate it, you look for what cancels out, and then you evaluate the limit. So since this is n squared and this is n squared, since they're the same, you just use the coefficients, which is the part out front. So it's going to be absolute value x minus 5 over 4. The absolute value of -4 would just be 4. So I just kind of took that out of there and just wrote 4. Like you evaluate that part. And then what's the rule? It has to be less than... one. Good. And then you're going to multiply the 4 over. So less than 4. And I just always draw a little graph because I think it helps to see the visual. This one is centered at 5. And you can go 4 units in each direction. So R is 4. So the values that we're going to have to test are 9 and 1. So we're like halfway done with the problem. Now we're going to test the 1 and the 9 and see if we include them or not. Okay, so we're going to plug in 1 for x. all the way back here in the original problem. So we're going to plug in 1 for x back to that thing. So if you plug in 1, you're going to have 4 times 1 minus 5 would be negative 4 to the n over n squared negative 4 to the n. Now that's actually kind of nice. I know that looks like a disaster, but what's going to happen? Yeah, those are gone. And so does it converge or diverge? We can actually just write the answer. Converges because p equals 2, which is bigger than. So that looked kind of scary, but it actually wasn't that bad. Which is typically how series go. They look awful, and it's all because of all the symbols and everything. It looks really horrible, but like the math that you're doing isn't actually all that bad. All right, so if you plug in 9, we're coming back up here to, again, the original problem. If you plug in 9, you're going to have 4 times 4 to the n over n squared. And then I'm going to rewrite that negative 4 to the n like this. It means the same thing, but why do you think I did that? Like, why did I separate it like that? Yeah, so that you can cancel stuff. So now it's not a P series, now it's an alternating series. We're past the AP exam. If you recognize that it's an alternating series, I'm fine with you just doing this. You don't have to write anything else. I don't care. Just recognize that it's an alternating series and then just say converges by
alternating series on the test.
Just write converges by alternating series. They always do. Oh, well, I guess I shouldn't say they always do, because if you do the limit as n goes to infinity and it doesn't equal 0, then it diverges by nth term test. It will, though. Just write converges by AST. Okay. So our interval of convergence, we get to keep both of them. So both of them have brackets. That was a lot of writing, but again, I actually kind of like those. I feel like they turn out the same every time. You set it up, you reciprocate, you cancel stuff out, you evaluate the limit, check your endpoints. Neither of those was too bad. Let's keep going. All right, you're given this function f of x. G is the integral of that. Oh, I messed this one up. It says find the first 5 non-zero terms. It should be 4. I don't know why I accidentally wrote 5. We find the first 4 non-zero terms. That's typically how those look. So I'm going to write my derivatives off to the side up here. So G prime is the first one that we need. If you do the derivative of an integral, it's just f of x, which is this 1/2 e to the negative 2x. And we're going to have to go all the way to the 4th derivative here. All right, so second derivative, it would be this. E is its own derivative, but then you have to chain on a negative 2. So negative 2 times 1/2 would be negative 1. And the third and fourth derivative, it's going to be the same thing. It's just you repeat that, but you have to multiply on a negative 2. So this one would actually be a positive 2 e to the negative 2x. And then what would your fourth derivative be? Yep, good. You just keep on multiplying on a negative 2. So again, the first derivative is this. And then you just keep doing derivatives after that. All right, again, if you don't want to, that's fine. But I always just write out the whole thing. Was this centered at 0? Yes, about 0. Okay, so that's a little bit shorter to write. So it'll be take 2. G of 0 over 0 factorial x to the 0. And then around 0, like, yeah, just say Maclaurin. Like, I don't get that either. Like, we have a word for that. So just say Maclaurin. Like, just say Maclaurin. Why would you say Taylor around 0? You know what that tells me, though? If you understand the material well enough to be annoyed by that, that means that you really understand it. Right, yeah, exactly. Yeah. So it says, right, the first 4 non-zero terms, but you're probably noticing we wrote out 5 of these, but that's because this first one, if you plug in 0, the integral from 0 to 0 is 0, so that one goes away, and it's the first 4 non-zero terms. So we're actually gonna start with this one. Okay, you don't have to simplify anything down, all right? G prime of 0, if you plug in 0, e to the 0 is 1 times a half would be a half. So 1/2 over 1 factorial x to the 1. Actually, we are gonna have to write the general term here, so it's better if you don't simplify, because then it makes it easier to see the pattern at the end. All right, so second derivative at 0, that would be -1 over 2 factorial x to the second. Third derivative at 0 would just be 2. And then fourth derivative at 0 is -4. So those are your first 4 non-zero terms. And then we need to write the general term for this. Now we got rid of this one. So this is the first term, this is the second term, this is the third term, this is the fourth term. So it's going to be n factorial in the denominator and then an x to the n off to the side. The only thing you really need to figure out the pattern for is this part, 1/2, -1, 2, -4. Again, I usually write like off to the side. That helps me like come up with a pattern.
Negatives today.
It'll be, see, there's different ways you can write it. I'm looking at how I have it on my sheet, how I chose to write it, but there's always kind of like different ways you can put it. Did you say negative n plus? Yeah, because it's gonna have to alternate. So we do need that. So I guess don't worry about these negatives now. Let me get rid of those because we took care of the negatives. But you need like some kind of pattern there. It's geometric. So you're going to start with the 1/2. And then what are you multiplying by each time? Like to get from 1/2 to 1, and then from 1 to 2, and then from you're multiplying by 2 each time. So it's 2 to the n minus 1. It's just a geometric thing. To be really honest, if you get all the rest of this, but not that, I would only take off like 1/2 point. Okay, like don't. Again, we're past it. Like I have to give this test and it covers this material, but at that point, like if you got this, I'm happy. Because we got rid of the 0th term, and you're starting with the first one. Because usually it's just to the n, but we like got rid of the first one. All right, this is your Lagrange error bound.
I don't even know if I have to.
Okay, so for this one, and we will need a calculator, and I'll let you use a calculator on the test. It's what is the degree? So n is something we don't know. We're going to figure that out. These are always Maclaurin. So c is 0. X in this case is 1.3. So the first part of the formula is the most annoying part because you can't get it. If you could, then there'd be no reason to estimate an error. So sometimes like the problem will give you a workaround, or they'll tell you what number to put there. You do the function to the c and x, like you plug both of those in and it's whichever one's bigger. Now this function is e. So e to the 0 would be 1, e to the power 1.3. It's going to be more than 1, but here I'll type it in for us. It is 3.669. So that's the number that's going to go there. And I have the calculator here and I just typed it in. That's all I did. And then it's x minus c to the power n plus 1. It's always the next term. And then over n plus 1 factorial. And we want that to be smaller than 0.001. Now here's the annoying part. You have to be like, what if n is 3? What if n is 4? What if n is 5? Until you get it to work. But you can just watch me type this in, and I just always like hit the back button and go back to what I had previously and just keep changing it. So let's try 5. I think it's higher than that actually. 5 plus 1, and your factorial is in the math menu under PRB. Okay, so I have all that typed in. I put in 5 for n. Is that smaller than this? No. Okay, so I'm going to go up and I'm going to just change the 5s to 6s. Is that smaller than this? No, I think it's 7, because that's pretty close. Once it changes it to a scientific notation, we know it'll be smart. You good. So 7. So n is 7 is the answer to the question. So you just keep typing it in until you get it to be smaller than whatever the number is. So this probably looks like the one you guys had on your test. All right, so the chlorine series for ln of x is given by this, right? The first 4 non-zero terms and the general term for f. This one's actually kind of nice because look, f is ln of x plus 1. If you plug x plus 1 in for all these x's, the plus 1 and the minus 1, yeah, are just going to cancel out. Like you would have x plus 1 minus 1 and x plus 1 minus 1. So it's just going to be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. And then we're going to write the general. So it alternates. You'll need that -1 to the n plus 1. And then what else? Yeah, x to the n over n. Yeah, that's all it turned out to be. So don't overthink that. All right, this one, we're told the radius of convergence is 1, determine the interval. Okay, so that means we're going to test -1 and +1 and just see what we can include. So we're going to plug in -1. Now, unfortunately, if you don't get part A, then you can't do part B. But this was like a pretty simple thing to get in this case, and it's like that on your test too. So we're going to have summation from 1 to infinity of this thing, and we're just going to plug in -1 for the x. So I'm putting -1 right there. Now I would combine the -1s together. When you multiply, you add your exponents. So it would be -1 to the 2n plus 1. And so then you have to think, does it still even alternate? Because sometimes it just turns out positive all the time or negative all the time. And sometimes it still alternates. So what do you think? You plug in any number for n. Will it still alternate or will it stay the same all the time? Yeah, it'll be negative all the time. So what I'll usually do is just move that negative out front of the whole thing. Like the entire thing is just negative now. Because it just makes it a little easier to notice what's going on. And so does that converge or diverge? Yeah, diverges because p equals 1, which is less than or equal. And then we're going to go back right here and plug in a +1. 1 to the n is just 1. So basically you can ignore that part at that point. Because it would be 1 times 1 times 1 times 1, which is just 1, and that's not going to change anything. So what do you notice about this one? Yay. Oh, and then I guess I should write the answer. Got all excited. I figured it out and I didn't write the answer. So -1 diverged. So that's a parenthesis. +1 converged. So that's right. And then last one. So write the first 4 non-zero terms for the Maclaurin series for f prime of t to the 3rd. And then it kind of changes after that. So what we're going to do is we're going to write f prime of x. We're just going to take a derivative and then we're going to plug in t cubed. Now, f is that thing that you wrote back in part A. We're just going to take the derivative of that. And it's actually a really simple derivative to take. What would be your derivative of just x? That'll be 1 minus, and then the 2's cancel, so it would just be x plus, and then the 3's cancel, so it would just be x squared. Do you get what I'm saying? Like all those are going to cancel. So it'll be 1 minus x plus x squared minus x to the 3rd. And then we're just going to plug t cubed into that. So it'll be 1 minus t cubed plus t cubed squared would be t to the 6th. And then t cubed be t to the ninth. You're probably like, you said I didn't have to simplify anything. Yeah, but I know that I'm gonna reuse that for the next thing, so it actually is good if you just multiply those numbers together. So g is given by integral of that, so we're gonna do the antiderivative of what we just found. And I think this one just says the first three non-zero terms, so you can kind of ignore that minus t to the ninth. We're gonna just do the antiderivative of this. So that would be x minus 1/4 x to the fourth plus 1/7 x to the seventh. This is basically just practice doing derivatives and antiderivatives is really all this is. They're calling it a Maclaurin series, but it's really just that function. Do a derivative, plug something in, now do an antiderivative. You're just practicing calculus. All right, and then it says to plug in 2. So we're just gonna plug in 2 for that. Oh, and I guess, and I wouldn't take off for this, but it's an approximation, so it should technically be the like wiggly equal sign.